In previous video, I explained the proof of this inequality of integrals. What does it states? If fx is bounded and integrable in enclosed interval AB, capital M and small m are bounds of fx in AB, then m into b minus a less than or equal to a to b fx dx less than or equal to capital M into b minus a if b greater than or equal to a, and m into b minus a greater than or equal to a to b fx dx greater than or equal to capital M into b minus a if b is less than or equal to a. Correct? This is the inequality that you have studied. Capital M into b minus a. If b is equal to a, result is obvious. Say this inequality is very important in Riemann integration, because while proving many results in many analysis of this real analysis or even complex analysis, we use this. Now this result is a corollary to that inequality. Now how to prove this one? What is given? Fx is greater than or equal to 0 for all x. Now proof of this is like this. Given fx is greater than or equal to 0 for all x belongs to AB. Therefore m is greater than or equal to 0. Because what is m? M is the lower bound of fx. Therefore m is value of fx in AB. Therefore m is greater than or equal to 0. Now take first result. Suppose b equal to a, result is obvious. B equal to a, result is obvious. Suppose b greater than a, then what happens? B greater than a, we have a to b f of x dx is greater than or equal to m into b minus a, because that inequality. For b greater than a to b fx dx is greater than or equal to m into b minus a. Now this is positive, m is positive, so here m is positive, b minus a positive, therefore it is greater than or equal to 0. This is the greater than or equal to 0. Important thing is m is greater than or equal to 0 here. Now b, second part, b is less than a, because b is equal to a, result is obvious. Suppose b less than a, then integral, we interchange a and b here. B less than a, integral b to a fx dx is greater than or equal to 0. Correct? Greater than or equal to 0. Now what you have to prove? A to b fx dx is less than or equal to 0 when b less than or equal to a. For that, suppose b less than a, as proved here, it becomes b to a fx dx is greater than or equal to 0. This implies, what is a to b fx dx? A to b fx dx is minus b to a. Again, definition of a to b fx dx when b less than a. A to b fx dx is minus b to a fx dx, and it is less than or equal to 0, because here b to a fx dx is greater than or equal to 0, minus b to a fx dx is less than or equal to 0. So this result is quite simple. It is, if fx is greater than or equal to 0, bounded and integrable, then a to b fx dx is greater than or equal to 0 if b greater than or equal to 0, b greater than or equal to a, less than or equal to 0 if b less than or equal to a. Now using this result, we prove next one important result. The result is like this. See, first I clearly write this result. We take this also a corollary. If integral a to b fx dx and integral a to b g of x dx both exist, then f greater than or equal to g implies integral a to b f of x dx is greater than or equal to a to b g of x dx if b greater than or equal to a, and integral a to b f of x dx is less than or equal to integral a to b g of x dx if b less than or equal to a. See, this is the result. What is given here? It is given both fx and gx are bounded and integrable, because both exist means bounded and integrable. Now, f greater than or equal to g implies a to b fx dx is greater than or equal to a to b gx dx. Now, when b less than a, using definition of integral a to b fx dx as minus b to a fx dx, we can easily prove second one. But the proof of this is important, because usually we take b greater than a always. B greater than a. B less than a, it is a particular case. First part we prove like this. We use for that previous result. What is given here? Given f is greater than or equal to g. Therefore, f minus g is greater than or equal to 0. This is the first thing. F minus g is greater than or equal to 0. Also, what are given? Fx. One more thing given is, we use this one, f minus g is greater than or equal to 0, first thing. Also, fx and gx are both bounded and integrable. Bounded and integrable, correct? Therefore, fx minus gx is also bounded and integrable. Bounded and integrable. Which result is used there? Algebra of integrable functions. If f and d are two functions such that both are bounded and integrable, then f plus d is integrable, f minus d is integrable, f into g is integrable, f by g is integrable. We have proved this one. So f minus g is bounded and integrable. F minus g is greater than or equal to 0. From previous result, both conditions are satisfied here. F minus g is greater than or equal to 0 and f minus gx is bounded and integrable. From previous result, integral a to b f of x minus g of x is greater than or equal to 0 for b greater than or equal to a, less than or equal to 0, b less than or equal to a. See the previous result. We make use of that result here. But a to b fx minus gx is a to b fx dx minus a to b g of x dx. It is greater than or equal to 0, b greater than or equal to a, less than or equal to 0 if b less than or equal to a. Now, this implies, what does this implies? A to b f of x dx is greater than or equal to a to b g of x dx if b greater than or equal to a, and a to b f of x dx less a to b g of x dx if b less than or equal to a. So the proof is we have used the previous result to prove this. Now we may come across these results in the future while studying further Riemann integration or improper integral. Improper integral means the extension of study of Riemann integration. There we may use such results. Finally, one important result that is important from examination point of view also. In the university examination it is often asked this, and I proved that one. That is the last result on inequality of integrals. Last what you call corollory. It states like this: if integral a to b f of x dx exists, then mod of integral a to b f of x dx less than or equal to mod of integral a to b mod f of x dx. So the result is like this, but this result is very important. The proof may be asked, or we use this result while studying further the Riemann integration. We may use this one, or we may use this one in if I remember correctly, then the complex integration also we use this inequality. Now it is the corollary to that inequality. What is the inequality? M into b minus a less than or equal to a to b f of x dx less than or equal to capital M into b minus a. This is the inequality. All the results are based on this. Now to prove this, what is given? To prove this, it is given integral a to b f of x dx exists. That means fx is bounded and integrable on closed interval ab. And we have studied this. If fx is integrable in ab, then mod fx is also integrable. You remember this result? I explained the proof of this. If fx is integrable, mod fx is also integrable. Therefore, integral a to b mod f of x dx exists. First result is mod fx dx exists. Now we have minus mod fx less than or equal to fx less than or equal to mod f of x. Straight away we can write this minus mod fx less than or equal to fx less than or equal to mod fx. Now we take first one, b greater than or equal to a, because two cases we have to take b greater than or equal to a, b less than or equal to a also. If b greater than or equal to a, then what happens? See the previous one. What does previous one states? If fx is greater than or equal to gx, integral a to b, if fx is greater than or equal to gx, integral a to b f of x dx is greater than or equal to a to b g of x dx. See the previous result. Therefore, if b greater than or equal to a, we can write here, minus a to b mod fx dx less than or equal to a to b f of x dx, a to b f of x dx less than or equal to a to b mod fx dx. Because using this result, I think this step is clear. Now see this one, it is of the form, if x is greater than minus a less than a, then we write mod x is less than a. Correct? So what does this implies? Mod of a to b f of x dx, a to b f of x dx less than or equal to a to b mod fx dx. Correct? A to b mod fx dx. Because of this result. But what is this a to b mod fx dx? It is positive. Because b greater than a here, this b greater than or equal to a, mod fx is always positive. So it is, we can write mod of a to b mod fx dx. Because it is positive. So mod of a to b fx dx is less than or equal to mod of a to b mod fx dx. Now suppose b is less than or equal to a. Equal to a, it is obvious. B less than or equal to a, as proved here, only thing is we interchange a and b. Mod of b to a fx dx less than or equal to mod of b to a mod fx dx. But what is b to a fx dx? B to a is minus a to b. Minus a to b fx dx is less than or equal to mod of minus a to b mod fx dx. But mod of minus is plus. So we have this plus. So these are some important results which can be derived from inequality of integrals. The last one is very important, and proof of any of these may be asked in the examination. So I think this topic is clear. The next topic is functions defined by definite integrals. I think functions defined by definite integrals. I explain here one definition and also give the one theorem statement only. Proof may not be possible in this video. I continue in the next video. What is the definition? Functions defined by definite integral. Now, suppose fx is bounded and integrable. Definition: bounded and integrable in AB, closed interval AB. Now, suppose t belongs to AB. T belongs to AB. We write phi of t is a to t f of x dx. Say a to t f of t may be any point belonging to AB. Then what is a to t f of x dx? It depends on pi. It depends on t. A to t f x dx depends on t here, because t is variable here. It belongs to AB. The value of a to t f x dx depends on t. So it is denoted by pi of t. And this pi of t is called integral function of. It is integral function of fx dx. It is integral function of fx. Fx is integrable function here. Fx is integrable function. Pi of t is called integral function of this integrable function. Now we study the property of this integrable function. In the first theorem we prove that this pi of t is continuous in closed interval AB. What is phi of t? It is a to t fx dx. It is called integral function of fx. It is continuous. Second, phi of t is differentiable in AB. Differentiable in AB. Then finally we state and prove fundamental theorem of calculus, which gives the relation between this phi of t primitive and fx primitive. That I do in the next video. Yes, thank you.